Welcome to Mahatma Education Society's e-learning channel. This is the second of a series of videos on Introduction to Mechanical Vibrations. The outline of the discussion will be recapitulation of last lecture and vibration system parameters. The recap. We have seen what is meant by vibration, difference between vibration and oscillation, goals of vibration engineering, causes, effects, uses, elimination or suppression of vibrations. Vibration system parameters. Any real physical vibrating system of any form can be represented by the combination of three basic elements. They are mass, spring and damper. The mass provides the inertia effects. In actual practice, the mass can be either of lumped form or it is a concentrated mass form, wherein all the points within the mass can be described by the motion of a single point, that is the center of gravity alone. So, the distance between any two points within the mass, lumped mass, will not change even after there is the application of force. We call it as a rigid body. The second type of mass in actual practice is the distributed mass, or it is having some characteristics of both spring and damper. It is flexible in nature. We as engineers try to use simple analysis and we convert the distributed masses into equivalent lumped mass for our analysis. So, the lumped mass will be represented by a block of mass and the motion of which will be described by the center of gravity. So, this will be characterized by the linear motion, that is the displacement as a function of time t. So, the unit SI unit of mass will be given by kilograms. If I am having angular motion of the mass about some axis, then we speak about a disk having angular motion theta as a function of time, and schematically in the side view we show it something like this. And the unit for the mass moment of inertia will be given by the second moment of mass about some axis, which is nothing but kilogram meter square. By virtue of the motion of mass, we have an energy that is called as kinetic energy, which is given by either half mass into the velocity square or half into the mass moment of inertia into angular velocity square, where this x dot implies the derivative of displacement with time, the first derivative, or in some books it is given by x dash. Likewise for theta dot, that is d theta by dt, which can also be represented as theta dash. How do we come across this equation? So, half m into v square has been arrived at from algebra principles or from calculus principles. Let us see how this has been derived from algebra. So, we can combine the work energy theorem and Newton's second law of motion. So, we have the work done on a body by a force which is moving the body by some displacement delta s is given by force multiplied by the incremental distance, that is the work done. And incorporating the Newton's second law of motion, we are having the force as mass times acceleration into delta s. From physics principles, we know the final velocity square is equal to the initial velocity square plus 2 times a times the distance covered. Now, we will write this A del S as V square minus U square divided by 2, and this can be incorporated in this equation. So we have the work done is equal to mass times V square minus U square divided by 2, and if we assume that there is no initial velocity which is equal to 0, I have this as half times mass into velocity square, which is also equal to the kinetic energy from work energy theorem. If I am referring to the calculus principles, then this is nothing much different. It states that the change of kinetic energy is equal to the work done on a body by summing up number of forces acting on it so as to displace it by a small distance. So this is equal to the integral of the summation of forces multiplied by the incremental distance ds. So this is equal to, now we can incorporate the Newton's second law of motion, mass times acceleration multiplied by ds, and the acceleration is given by the time derivative of velocity multiplied by ds. Now we rearrange this and we will write these two parameters as one thing. So ds by dt is given by the velocity, the time derivative of displacement. So I will be writing here the mass, let us take it outside, it's a constant value, so v times dv, which is given by mv square divided by 2, or half mv square. So basically we are having the same equation from both of these principles. Now spring. A spring is an elastic member which absorbs the shocks or impacts or jerks. So the spring is denoted by a helical spring, and it is defined by the force required so as to deform it by unit value. So I can denote the unit for spring as Newton per meter, and the parameter used or the symbol used for this is K, that defines the stiffness. Likewise, I can talk about the angular deformation. So in real case I can have the spring given by a shaft which has the spring properties, and this is defined by symbol K suffix T, that is torsional stiffness. So we can also denote the torsional spring, something of this kind. So the unit for this is Newton meter per unit radians, that is, it is defined by a torque required for causing unit angular deformation, and the unit of angular deformation in SI units is radians. So by virtue of the deformation of the spring, we have the internal resisting strain energy, and which also is called as the potential energy. So I know that by virtue of the spring I can have potential energy, and we also have potential energy by virtue of the mass. When there is a height difference from one position to another position, which is given by the mass times acceleration due to gravity into height difference. So this equation of potential energy for mass, that is mgh, may not always be present even though there is a mass. So we will see while solving the numericals. So we have to look at the configuration of the system. This might be present in cases such as pendulum, while it may not be present for masses which are oscillating about a pivot point, but which themselves are horizontal in position. The spring always has a potential energy, and this is given by half times the stiffness times the deformation square. So let us see how this equation has been derived. We know from the strength of materials the plot or the behavior of the spring parameters, that is the spring force versus the deformation. So deformation here I am denoting by x, which is nothing but the displacement of the mass that is transferred to the spring. One end is fixed and other one is connected to the mass, which is having a moment of x, hence the deformation becomes x. Now the plot is something like this. For a range of x, I have the force to be linearly proportional to the displacement or the deformation, and if the deformation is very large, then it becomes somewhat non-linear. The same case when we are applying a compressive force. So it is something kind of a S-curve. As engineers, we always try to simplify the problems, and instead of solving the non-linear problems, we concentrate on solving the linear problems. So non-linear problems will be dealt with in higher studies and is beyond the scope of our study. So we will just focus our attention on this linear laws, right? So the stiffness, the slope of this straight line is given by the stiffness of the spring. So I am having spring force proportional to the displacement or deformation of the spring, and I can convert that into an equality sign, and I can introduce a constant which is called as the stiffness, right? Now I am having the work done during the deformation, which is nothing but the internal strain energy that is given by the area under the straight line, right? So which is nothing but the area of the triangle. So it can be given by half into the spring force into deformation, while the spring force can be given by the definition of the spring, that is k times x into x, and ultimately I am having half k x square as the formula for potential energy of the spring. Next, we have the damper. Damper is in many textbooks or sources also called as shock absorber, but the role of shock absorbing is done by the spring in fact, and not by damper. So the name shock absorber given to the damper is a misnomer. It is inaccurate. Misnomer. It is inaccurate. So the damper is the technically correct word of describing it. The role of the damper is to dissipate the energy from the vibrating system into the surroundings. So there is a conversion of kinetic energy to the thermal energy. There is a fluid friction happening by virtue of shear effects within the fluid, and the heat created will be thrown out of the system to the surroundings through the cylinder walls. So this is represented by a piston. This is a piston rod, this is a piston, this is a cylinder, right? So this is a schematic representation, and this is defined by a constant called as damping coefficient, that is the damping force required per unit velocity. So it's a function of the relative velocity between piston and cylinder. So the unit will be Newton per meter per second, that is the velocity. So we take the second to the numerator and we have the meters in the denominator. So it's Newton second per meter as a unit for damping coefficient. We also can have the torsional damping coefficient in case I am having the angular motion of the piston with respect to the cylinder. So this will be given by, instead of force per unit linear velocity, we are talking about the torque per unit angular velocity. So Newton meter is the torque per unit angular velocity will be radians per second. So here there will be radians per second, second will go to the numerator, I will be having Newton meter second per radians. Okay. Now what is the energy associated with damper? Now the piston is moving by some distance from one position to other position in relation to the cylinder. So there is some work done by the damper so as to move the piston from one position to other position. So what is the work done? So we can say work done by the damper to dissipate the heat is equal to minus integral x1 to x2. These are limits of the position of the mass, position of the piston with respect to cylinder into Cx dot dx. So Cx dot is nothing but the damping force, which is a function of velocity, and it is the incremental distance between two positions, right? So this is a force multiplied by displacement, which is nothing but the expression of work done. So the reason why we are putting minus over here is because when the piston is at the initial position, there is a increased energy in the system compared to the final position of the piston, right? So there is a decrease in the amount of energy from the initial position to final position. So as to make the overall work done as positive, we need to associate this negative sign to this equation. So this term, integral term, is itself negative because the energy in the initial position is more than the final position, which is giving us a negative value, multiplied by the negative value over here will give us a positive value. So this is the standard formula for the work done by the damper. Now, what made springs and dampers necessary in mechanical systems? We will take one small example. You can assume very olden days people used to travel from one location to another location by means of, say, bullock cart, so which is primarily a mass. Inherently we also have the stiffness and damping properties, but let us assume that we have only mass for now. So this is the, let us say, the bullock cart, primarily concerned with mass. So what happened if there were disturbances on the road surface? So we have some peaks and troughs over here. Now what happened when the vehicle used to travel through this, on this road? So there were a lot of jerks happening, and it was very uncomfortable for the passenger, right? So to minimize this problem, subsequently people used springs which try to absorb the shocks. Fine. So I am having mass and some springs of some nature, and this was giving us a bouncy kind of effect, right? So because of the springs we had the bonding and rebonding of the masses, and hence we were having the oscillations taking place. Now what was the problem? Why not we are settling with the spring at the mass, and why dampers are required, right? So the problem is, this is something kind of a roller coaster ride, and again it was some sort of uncomfortable for the passengers. So once there is some disturbance experienced, you are having continuous movement of the mass, to and fro movement about the equilibrium position, and it was taking long time for the mass to settle out. So it was also not comfortable for the passengers. So it was required that there should be some means so as to dissipate the energy in the system, the vibration energy, and dissipate in the surroundings, so that this amplitude initial ones will be minimized. So within 1 or 2 cycles the mass was required to settle down to its rest position. So thereby people introduced different forms of dampers. So initially dry friction dampers were being used. Later on there were some research going on in this field, and people came up with the viscous damping, which was far more effective than the other types. So damper was required to dissipate the energy in the form of heat to the surroundings, and thereby the effect of that was to reduce the amplitude from initial cycle to minimum one. So within 1 or 2 cycles we were expecting that the mass should be settling down. So in this lecture we had seen what are the basic components representing any vibrating system: the mass, spring and damper, and what is the necessity of using the spring and damper in mechanical systems.